Hi students, today we shall see the next point of memory management, that is page replacement policies. Due to the concept of demand paging, the degree of multiprogramming can be increased. That is, more number of processes can be allocated in the memory as compared to the simple paging concept. What is demand paging? We have seen in the previous lectures. So we know that we can increase the degree of multiprogramming. Increasing the degree of multiprogramming means bringing in more number of processes in the memory. This can be done with the help of paging. When a page fault occurs during the execution of a process, a page needs to be paged into the memory from the disk. What is a page fault? Whenever we want a page to execute an instruction and that page is not available in the memory, we say that there is a page fault. So when there is a page fault during the execution of a process, the page which is not there in the memory has to be brought in the memory from the hard disk. However, it may be the case that there is no free frame in the memory. So if we want to bring the new page into memory, a frame in the physical address should be free. If it is not free, we cannot keep the new page. In such case, an already existing page should be replaced so that there is no room for a page that needs to be paged. So if we want to bring a new page into the memory and the frames are not free, we have to write back or replace an existing page. This is known as the page replacement. Suppose a page is used frequently during the execution of the process. If this page is replaced by a random approach, then it may be needed very soon and need to be paged in again, resulting in more page faults and degrades the performance of the system. Thus, instead of replacing any page, the use of pages in the memory is to be observed and page should be replaced such that the effect on performance of the system is the least. The strategy to choose the best page to be replaced in the memory is called a page replacement algorithm. In an operating system that uses paging for memory management, a page replacement algorithm is needed to decide which page needs to be replaced when a new page comes in. When a page fault occurs, page fault routine locates a free page frame. There is a possibility that the memory is full, that is, no free frame is available for allocation. The operating system has to remove an existing page from the memory to make space for the desired page to be swapped in. The page to be removed will be returned to the disk depending on whether it has been modified or not. This is known as page replacement. The strategy to choose the best page to be replaced in the memory is called the page replacement algorithm. The algorithm that will produce less page faults will be considered a good page replacement algorithm. A string of memory references is known as reference string. The page number containing the memory references is taken as the reference string. The number of page frames plays an important role in producing the number of page faults and in the performance of the system. The more the number of page frames, the less is the probability of page faults. and increased performance of the system. This is because with the increase in the number of page frames, more number of required pages can be accommodated in the memory. So if we have more page frames in the physical memory, we can write in more pages into the memory and can execute more number of processes. Thus we can increase the degree of multi-programming. A page replacement algorithm must satisfy the following requirements. The algorithm must not replace a page that may be referenced in the near future. This is known as non-interference with the program's locality of reference. What is locality of reference? We have seen in the previous lectures. So the pages which we will require in the near future has not to be replaced. The page fault rate should not increase with an increase in the size of memory. So we shall see the first page replacement algorithm, that is first in first out. This is the simple page replacement algorithm. So the most simplest page replacement algorithm is FIFO, that is first in first out. When a page needs to be replaced, page in front of the queue is selected for removal. So for this first in first out, we are going to use data structure queue. The page which is in front of the queue will be replaced first. In this algorithm, a queue is maintained. The page which is assigned the first frame will be replaced first. Now we shall see an example of how FIFO is implemented. To illustrate the page replacement algorithm, we shall use the reference string. So to understand how the first in first out policy or algorithm works, we are going to take an example. This is the reference string, that is the page numbers which will be referenced by the CPU. So if we are going to use the FIFO, the reference string, first the 3 frames in the physical memory are empty. We are taking an example with 3 frames. Our 3 frames are initially empty. So if we are using the first in first out method, the first 3 pages for the first 3 faults will be placed in the memory. So page number 7, page number 0 and page number 1 are placed in the 3 empty frames, are brought into these empty frames. Next page to be referenced is page number 2. So page number 2 we have to bring in memory, but now all the 3 frames are engaged. So for that, to bring page number 2 in memory, we have to replace one of these 3 pages. But now we are using first in first out algorithm. So among these 3, who was the first? 7 was first. So we shall replace frame number 7 with page number 2. So 7 will be replaced by 2. Now we are going to have 2, 0 and 1. Next page to be replaced is 0. There will be no page fault since page number 0 is already in memory. Next reference is page number 3. So for page number 3 there will be a page fault since it is not there in memory. Now we have to bring page number 3 in this frames. We will be using FIFO. So among these 3, who came first? So 0. So now we are going to replace 0 with 3. So now the frames we will have 2 as it is. 0 will be replaced by 3 and 1 will remain as it is. Next page frame is 0. Again there will be a page fault since page number 0 is not there in memory. So among these three, who was the first who came? It was page number 1. So we will replace page number 1 with page number 0. So now we can see 2 is over here, 3, and 1 is replaced by 0. Now next page, page number 4. Page number 4 is also not there in memory. Again page fault. So to bring now page 4 in the memory, we are going to replace page 2, because among these three, first page which came was page 2. So replace 2 with 4. So 2 is replaced with 4, 3 will remain as it is, 0 will remain as it is. Next page, again page fault, will require 2. It is not there in memory. Among these three frames, page number 3 came first, so replace 3 with 2. So 4, 3 is replaced with 2 and 0 remains. Next page is page number 3, again page fault, so we'll replace 0. So 4, 2 and 3. Page number 3 already in frame, no page fault. Page number 2 already in memory, no page fault. Page number 1, it is not there in memory, so page fault will occur. Now among these three, who came first? 4. So we'll replace 4. Okay, so 0, we have missed with this 0. So 0, 2, 3. 3 is already over here, 2 is already, so 1 we are going to replace with 2. Next is 2, again we will replace with 2, and so on. We'll complete with this reference string. So for using FIFO, to implement this algorithm, each table entry includes the time when the page was swapped in the memory. This first in first out policy has one anomaly that is known as Belladie's anomaly. Usually we think that if we increase the number of page frames, the number of page faults will be decreased. But in case of FIFO, it is not the same. What happens is opposite, and that is known as Belladie's anomaly. FIFO page replacement algorithm suffers from Belladie's anomaly, a situation in which increasing the number of page frames results in more page faults. Okay, that is why FIFO policy has this one anomaly. Next we'll move on to the second page replacement algorithm, that is optimal algorithm. In this algorithm, pages are replaced which would not be used for the longest period of time in the future. The practical implementation is not possible because we cannot predict in advance those pages that will not be used for the longest time in future. This algorithm leads to less number of page faults and thus is the best known algorithm. The advantage of this algorithm is that it causes least page faults as compared to other algorithms. Now we'll take the same reference string and see how this optimal algorithm works with 3 frames. Initially the 3 frames are empty, so the first 3 pages with first 3 page faults move into these empty frames. So 7, 0 and 1. In this case we replace the page which is not used for the longest duration of time in the future. So now for the fourth page, that is page number 2, has to be brought inside the memory. Now among this 7, 0 and 1, which will be replaced? So we are going to see the future, that is the forward reference string. Which page will be referenced last will be replaced. So 0 will be faulted as soon, next will be 1 and 7 will be the last one which will be referenced. So we will replace 7 with 2. Okay, next page 0, no page fault since page number 0 is already in memory. Next we will require page number 3. Page number 3 is not there in memory, so there will be a page fault. Now among these 3 page frames, which will be replaced? Now we have to see the future reference string. 0 will be referenced soon, after that 2 will be referenced, and 1 will be the last one which is referenced. So we will replace 1. So we have replaced this 3 with 1 with this 3. Next page which is required is 0. It is already in memory, so no page fault. Next is page number 4. So it is not there in memory, there will be a page fault. So now we are going to see the next future. 2 will be referenced soon, 3 will be referenced soon, and last which will be referenced is 0. So we will replace 4 with 0. So now 0 will be replaced with 4. Next page reference is 2, which is already in memory, no page fault. Next is 3, no page fault. Next page to be is 0, it is not there in memory, so we have to replace someone from 2, 4, 3 for making space for 0. 3 will be referenced soon, 2 also will be referenced soon, 4 will not be referenced, so we will replace 4 with 0. Okay, so next page 3 already in memory, 2 already in memory, 1. So now we have to make space for 1. 2 will be referenced soon, 0 will be referenced, so we can replace now 3. So 3 is replaced with 1. Next page is 2 already in memory, 0 already in memory, 1 already in memory, 7 has to be replaced. So among these 3, who is going to be referenced? 0 is to be referenced soon, 1 will also be referenced, so 2 can be replaced. So 2 is replaced with 7, 7, 0 and 1. So there will be total 9 page faults. So this is the algorithm which has the least number of page faults. Next we will see least recently used algorithm. In this algorithm, page will be replaced which is least recently used. The memory management hardware uses a counter which is incremented during each memory reference. Each page table entry has a field that stores the value of the counter. When a page is referenced, the value of the counter is stored in the page table entry for that page. The least recently used algorithm searches the table for the entry with the lowest counter value and selects that page for replacement. So in this case, in the least recently used algorithm, the page which is least used in this recent will be replaced. We shall again take the same reference string and see the example. Initially 3 frames are empty. We are going to put the first 3 pages in this first 3 frames. Next we have to make place for page number 2. So now which page will be referenced? Now in this case we are going to see the in the last optimal algorithm we used to see the future. In this case we are going to see the history. So which page was least recently used? 7 was least recently used. So we will replace 7 with 2. 2, 0, 1. Next page is 0, already in memory. Next page is 3. We have to make place for 3. Which page among these two was least recently used? It was page number 1. So we'll replace page number 1 with 3. Okay, 0 is already in memory. Now we have to make space for page number 4. 0 was least recently used, 3, 2 was the last one which was reference. So we will replace 2 with 4. So 403. Next is 2. So we have to now make space for 2. 4 was used, 0 was used, 3 was the last one. So we'll replace 3 with 2. Again page number 3 has come. Have to make space for 3. 2 was used, 4 was used, and 0 was used least frequently. So we'll replace 0 with 3. So again now we have to make space for page number 0. Now among 4, 3 and 2, which was the last recently used? Page number 4. Replace page number 4 with 0. 0, 3, 2. Next is page number 3 already in memory. Page number 2 already in memory. Page number 1. So we'll replace now the last one over here, 0 with 1. Page number 2 already in memory. Now we have to make space for page number 0. So we'll replace it with 3. 3 is replaced with 0. 1 already in memory. Now we have to make space for 7. So among these 3, who was the least recently used? It was page number 2. Okay. So in this way we are going to replace the pages. In least recently used, we will require 12 page faults. So compared to the first in first out optimal NLRU, optimal algorithm will have the least page faults. And the last one, similar to least frequently used page replacement algorithm, is the most frequently used algorithm. This algorithm is based on the argument that the page with the smallest count was probably just brought in and has yet to be used. It is completely opposite to LFU. So these are all the page replacement algorithms. Thank you.